This is part 2 of simplifying trig expressions using identities. So these hints that we have on this particular sheet, these are all the hints I can give you to do all 30-something problems that are on worksheet 6. So sometimes it's going to be helpful to turn things into sine and cosine. You'll see what I mean when we get there. Second thing, if I'm ever dividing by something, a lot of times it's easier to multiply by its reciprocal as opposed to having a fraction over a fraction. You'll see what I mean as we get to some of the problems. Lastly, or not lastly, but never leave a trig function in the denominator. If you have something in the denominator, move it up by using its cousin, its reciprocal identity, one of the ones that we wrote down earlier. If I see something in the denominator, it's better to write it as tangent instead of cotangent in the denominator. That's what I mean by that. When there are two terms and one of them is a trig function squared. If you have a secant squared of theta minus 1, turn that into whatever it is using that Pythagorean identity. Substitute. This is an easy way for us to go from two terms down into one term, is by using those Pythagorean identities like we practiced last time. And then I wrote here, factoring is going to help, and so is foiling. And if you need to review how to do factoring, look at the notes from 1.2 and 1.3. Let me minimize this. I was looking back, way back in Unit 1. Boom, way back here. 1.1, 1.2, 1.3. This is the stuff that we covered. This type of factoring, this type of factoring. We covered this type of factoring. And so I wrote down the references to 1.2, 1.3, and how to foil. How to foil. It's all there because we covered it a long time ago. But if you forgot where to look, I put down the notes for you to double check as we go along. Okay? So those are my hints. Let's go and do some examples. I have 5 examples that I have picked for you to do. If you want to do them in your packet, you are welcome to do so. Or, if you want to do them in notes, you're welcome to do that as well. We are going to do number 11 first. Number 11 says the sine of theta divided by cosecant of theta. Now you can do this in a couple different ways, but I'm just going to show you what I do. And I could do this in a, well, here's what I'm going to do. Equals. I have my sine of theta. I'm just going to leave that in my numerator. And then what I'm going to do, instead of dividing by cosecant of theta, I'm going to divide by its reciprocal. I'm going to put 1 over sine of theta, but that's in the denominator, so I'm just going to make that 1 over sine of theta like that. And earlier I gave you a hint. My hint was, instead of dividing by something, it's sometimes easier to multiply by its reciprocal. So this is the same thing as the sine of theta multiplied by the reciprocal of 1 over sine of theta. Now I'm not sure if you know what sine of theta times sine of theta is, but I do know what that is. It's sine squared of theta. And that's what this simplifies to. Some of you might think, oh, I could make that 1 minus cosine squared of theta. Yeah, you could, but that's not really more simplified. If you can get it down to one term, perfect, that's your goal. Your goal is to get this as small as possible. This is as small as I can make it. I don't want to make it bigger. I want to do this in one other way, so I'm going to switch colors of my pen. show you that I could have done it one other way, just in case you think about it, like this. Earlier, I told you that you could move this from the denominator to the numerator, and you could have had sine of theta times this one, sine of theta. And that would have been the same answer, by the way. So if you don't want to switch it to 1 over sine of theta in the denominator, you can move it straight up right away and know that you'd have to multiply it to get to sine squared of theta. And that's your answer. Pretty basic. That's as easy as it gets. They do get a little bit harder. 16. Next question. 1 minus cosecant squared of theta. This has a squared term in it. If there's a squared term and there's an additional term, there are two terms here. So this goes with when there are two terms and one of them is a trig function squared, substitute using a Pythagorean identity. Which ones am I referring to? I'm referring to one of these ones. So I'm going to have to look at these and look for something that deals with either this one or this one, which is why it is helpful for you to have these things memorized. Let me show you what I mean. There is a trig function that deals with cosecant squared. But if I don't know what it is, it's really hard for me to go, what are they doing? Let me write them down. Okay, I know what sine squared is. 1 plus cotangent squared of theta is equal to cosecant squared of theta. I know that. I've memorized it. I'm hoping you have too. If you haven't, you might need to do some flashcards and memorize those things. So that means if I know that this is my Pythagorean identity number 3, whatever it is, the third one, and I have 1 minus the cosecant squared of theta, and they've subtracted cosecant squared and subtracted cosecant squared of theta. And they have this side by itself. Wait a second, there's a 1 minus cosecant squared of theta plus cotangent squared of theta equals 0. What did they do to get it by itself? They must have subtracted cotangent squared of theta to the other side. What does this simplify to? My answer, this simplifies is equal to negative cotangent squared of theta. You will never, I'm not going to say never, you will hardly ever use the Pythagorean identities with all 3 terms. You will take it to go from 2 terms down into 1 term, just like that. And so it's really helpful to know which one's which. And the way that I remember this, believe it or not, is that the cotangent and the cosecant are co-captains. They're the ones in the formula together. Sine and cosine are together, and tangent and secant are together of our 6 trig functions. The next one I chose for you is 21. Both of these have 2 terms. You cannot simplify top to bottom here. We can't do this up and down because then we would be breaking order of operations. So don't try to reduce. I'm going to put this, cannot reduce yet. Cannot reduce. This is in parentheses. This is in parentheses because that line means that this is in a group. You cannot do division before you do what's in the group. You cannot reduce. So what I'm going to do here is I am going to try to convert these using my Pythagorean identities again. The 2 Pythagorean identities I'm going to use. there is a formula that deals with tangent squared of theta. Let's see if we remember. Plus 1 is equal to blank. If you know what it's equal to, tell the person you're sitting next to, please. Good. And the second Pythagorean identity that I'm going to use has something to do with this. It's the sine squared of theta plus the cosine squared of theta is equal to blank. Tell the person you're sitting next to what it is. So we're going to use these two identities. How am I going to use them? I need to figure out what secant squared of theta minus 1 is. And some of you will be able to do this part in your head now. You'll be able to look at this and go, oh, they subtracted 1 from both sides. I know what secant squared of theta minus 1 is. It's equal to something. Tell the person you're sitting next to what you think it is. It's equal to tangent squared. So instead of this for my numerator, I can now write tangent squared of theta. Now the cosine squared minus 1, some of you will be able to do this in your head. You're going to subtract 1, but then you have to move the sign over here by subtracting sine squared of theta. What is the cosine squared of theta minus 1 going to be equal to? Negative sine squared of theta. Now that we have that, I still have two terms here. It is not simplified enough. We're going to try to see if we can get it down to one term. So here's what I have. I have tangent squared of theta divided by sine squared of theta. This is why sometimes it is helpful to convert things into sine and cosine. Let's switch this tangent squared of theta into sine squared of theta divided by cosine squared of theta. I'm going to change this numerator into sine squared of theta divided by cosine squared of theta. And that is all over negative sine squared of theta. Why is that helpful? It's helpful because then maybe something will simplify with the sine squareds. Let's see. Sine squared of theta over cosine squared of theta, but instead of dividing by sine squared, I'm going to multiply by the reciprocal. I'm going to multiply by sine squared negative sine squared of theta in the denominator. You see it? I was dividing by this, but now I'm multiplying by 1 over sine squared of theta. This is where it gets a little bit, oh, look at this, whee, goes away. That's so satisfying when things cancel out like they're supposed to. Equals. Positive times a negative is a negative 1 over cosine squared of theta. And you're finally down to just a cosine squared, but you're never going to leave your answer like this because you never leave your answers, your trig functions in the denominator. There's a way to move this up. This is cousin. This is the reciprocal identity to which trig function? And don't forget it's negative. Your final answer is negative secant squared of theta. Now I need a show of hands. I did 21. 21 is like a pretty medium level problem. If you understood what I did and how I got there, please raise your hand so I can see how many understand what's going on. Not bad. That's pretty darn good. It's pretty darn good. I like what I see there. The reason why I'm going to put you into groups today is because some of you are going to get this right away and some of you are like, I need somebody to explain it to me, and that's why I'm going to put you in a group situation so you can see some of these things. I have two more examples. We're done with these two examples, then we'll get into the group work. I see several things that I could do with 26. I have a couple different choices. I'm going to do what I think I see first. I could factor is method number 1. I'm going to put over here just factor. Or what I could do is I can convert to sine and cosine. There's two things I see, two ways I could attack this problem. To factor or to convert to sine over cosine. I'm going to start with this one because some of you I think will probably do this first. This is what I think most of you will do. Cosine squared of x plus, what's tangent squared? If I were to convert it using its quotient identity, what does that equal to? So that's what that is, and I'm going to multiply it by the cosine squared of x. You could do that. And then, since you're multiplying, cosine squared of x goes into cosine squared of x one time. That means you are left with cosine squared of x plus sine squared of x, which is equal to, what does that simplify to? You use Pythagorean identity number 1. That's so satisfying when it just simplifies like that. Feels so good. Now, just so you know, you could have also done this a different way. I want to show you the factoring method, just in case. What if you saw a greatest common factor of a cosine squared? What if I did a cosine squared of x and I factor that out of these two terms? You know what you'd be left with? 1 plus, this times this is this times a tangent squared of x. This times this is that, this times this is that. And you know what I see when I see this? Oh, this is one of my Pythagorean identities. 1 plus tangent squared is secant squared. I know what secant squared is. It's 1 over cosine squared. Cosine squared times 1 over cosine squared is going to equal the same answer. It doesn't matter if you factor or if you convert, you'll get to the same answer. There are multiple ways to solve these problems. Just because you do it one way doesn't mean that's the only way. So I have to be flexible on what I accept as far as how you get there. But if we all use the same properties, we will all end up with the same answer. How do I know when to stop? A lot of times people ask me that question. Most of these will get to a single term, like a sine squared or a negative sine squared or a 1 or a 0 or something along those lines. Okay? Last one, number 29. Number 29 says cosine of k plus the sine of k. I know that looks like sink. Every time I wrote it down, I thought, man, that looks like sink, but it's not. When you see this, what I do need you to remember is that you do need to FOIL it out. You have two sets of these things, and you cannot just square each of these terms. You have to remember that you have two groups that are multiplying each other, and so that must mean you have to FOIL first times the first, cosine squared of k, first times the second, plus sine of k cosine of k. Going to switch colors now. if it'll let me, plus another sine of k cosine of k, plus another sine squared of k, plus another sine squared of k. So when I put all this together, if you FOIL it out correctly, you're going to get that you have cosine squared of k and then 2 of these plus 2 sine of k cosine of k plus sine squared of k. And that's important because you have these extra 2 terms that are in the middle. Can I rearrange addition and subtraction? I can do those in any order I want? Sure. Do you know what the cosine squared of k plus the sine squared of k is going to be equal to? Pythagorean identity number 1 says it's going to equal 1. Plus 2 sine of k cosine of k. Now, you might think that you can do something else with that. Turn it into a cosecant and stuff like that, but nothing right there is going to simplify any further than what it is. Like, it doesn't become anything else. Not until you get into AM and you're going to learn something called a double angle property, and we're not going to go there this round. That's where we end our answer for number 29. So I hope that these examples help you. I'm going to end the recording right there.